Hi everyone. Today we will be discussing, and as from my earlier videos, we'll be continuing basically another example of the electrical power and load calculations for data centers. Like earlier, we were discussing about smaller sized IDF rooms or data center closets, especially in big buildings. You have a couple of floors being managed by an organization, and they have their servers in a room, and you manage the IT room. And those are smaller size, about 1,000, 2,000 square feet of area, and we calculated the different cooling loads and the power calculations. But today we will be actually taking up larger square areas for data centers for organizations such as Amazon, Facebook, Google. These organizations deal with massive millions and billions of users globally. They have requirements for larger processing and larger data to be calculated, large amounts of storage required, and processing speeds. So, obviously, first thing, top of our mind, these are tier 4 data centers with full redundancies because even couple of minutes or hours of downtime could mean millions or billions even in losses, and we don't want that in these data centers. So if we consider these big data centers, which are hyperscale cloud facilities, and these are tier 4 data centers, and if their size, if we can consider, is about 100,000 to 200,000 square feet of area. And if you're considering racks, they could go from 1,000 racks to maybe even 5,000, 10,000 racks, depending on the storage. And cooling and generator sizing, we will also discuss these in the design, which I will also be sharing. So if you're considering from today's learning point of view, we will be designing a 100,000 square feet of data center area. And if we are calculating for about 1,000 racks and completely DX cooling, and if we take our first, like in the smaller data IDF closets, about 2,000 square foot of area, we had calculated and we had used up servers from Dell. And if you're considering the same servers, Dell servers with power of 500 watts, 0.5 kilowatt servers, again, if you consider two servers or n number of servers, here we will consider for design purposes two servers from Dell, both zero point 0.5 kilowatt, and a storage array of 600 watts, and we'll consider two storage arrays just for design purposes. They could be hundreds. So 600 watts, 0.6 kilowatts. So that's the power usage item list. So total. So if you're considering 1,000 racks for this large scale data center, 100,000 square feet, and if you're considering 1,000 racks, let's consider the power calculations for one rack first. So in one rack, if you're putting in two Dell servers and two storage arrays, having a power rating of 0.5 kilowatt and zero point 0.6 kilowatt. So four, if you're calculating for one rack, this is for design purposes, is 2.2 kilowatt per rack. And if you have 1,000 racks, so now you have 1,000 times 2.2 is 2,200 kilowatt. That's the critical load. So that's the main load for this 100,000 square feet of a data center. And then if that was step one, power usage for one rack times number of racks in that data center initially proposed. 1,000 racks, one rack is 2.2 kilowatt, 2,200 kilowatt. That's critical load. Next is the expansion, future load. We are considering 30% growth. Suppose it's a fast scaling organization and is trying to scale big. And it could be anything. It could be Netflix. It could be any kind of data center, and it's scaling big. It's huge. It's got a huge user base and it's growing. So future load, 30% growth. So we have a critical load of 2,200 kilowatt. And then the future at 30% is 2,200 plus 30% of 2,200 is 660. Okay. So that will give us 2,860 kilowatt or 2.86 megawatt. That's the future load, including the critical load. And the future load with the 30% addition, original critical was 2200. You're adding the future load 30%, 660. 2200 plus 660, 2860. It's going to be 2.86 megawatt. That's the total load, critical load, including the future. If you have a peak power multiplier with 5% overhead, remember, if you give 5%, it's 1.05. You multiply it. If it's 10% overhead, you give 1.1. So you're giving 5% overhead, 1.05. And after multiplying 2860 times 1.05, you have 3003 kilowatt or 3.0 megawatt. That's the peak power drawn. And the peak power adjustment is 3003 minus 2860. That's 143 kilowatt. Okay, that's the peak power adjustment. So step one was the total power usage for one rack times 1000 racks or number of racks. That gives you the critical load. 30%, 40%, whatever feature load. Here we have considered 30 times 30, 2860 you get, and you have a peak power multiplier 1.05. That's because of 5% overhead. You can have 10%. And then you have peak power drawn number, and you have peak power adjustment. That is the peak power drawn minus the future load. And then you get the peak power adjustment. So this is important for our calculation. Step 3, we got the rack with has servers, storage arrays, and number 1000 racks. You get the calculation. You have the future load, peak power multiplier. And now step 3, UPS load calculation. If you're assuming your UPS is 90% efficiency, that is for 100 watts, you're getting 90, for 100 kilowatt, you're getting 90 kilowatt output. Power losses from batteries due to charging issues and other inefficiencies, let's consider 20%. We can estimate UPS and batteries. That's 10 plus 20%. That's going to be 30% total inefficiency. 10% inefficiency due to the UPS, and then 20% for the batteries. So total inefficiencies is 30%. Now, step 4, the final load calculations. So here you have the critical load, that is was 3003 kilowatt or 3.003 megawatt. Mega is 10 raised to 6, kilo is 10 raised to 3, just for those who don't know. Inefficiency factor, we calculated 10 plus 20, 30% of the critical load. So that gave is 3003. That is the final load, actually. 3003 times 30 by 100, 30%. And you have a total of 900.9 kilowatt. That is 900 kilowatt or 0.9 megawatt. Okay, so that's the final load. So coming to the next, we got the racks, we got the future load, we got the UPS. Now we have the lighting load. Lighting is 1.5 to 2 watt per square feet, because nowadays we have more efficient lighting systems. Lutron is one of the automated lighting system, Lutron. If you're using more efficient lighting systems, you can assume 1.5, 2 watt per square feet. We're considering 2, just to be, considering the maximum, 2 watts per square feet. So 2 watts into, we have a data center of 100,000 square feet. So 2 watts into 100,000 is 200,000 or 200 kilowatt. That is the lighting load. So 6th step, calculating the total load now. So if you consider all the total load calculations, number 1 is critical load, 2200 kilowatt. You have the future load, 660. That was 30%. And then you have the peak power multiplier, 143. And then you have UPS and battery losses, 900 kilowatt. And then you have the lighting load of 200 kilowatt. So totaling all this, 2200, 660, 143, 900, 200, you get 4103 kilowatt, 4.1 megawatt to cool. So that's the total load. That means you need to bring in cooling to that data center to cool what amount of load? 4.1 megawatt. So you need to cool the heat generated by the equipments, and that load is 4.1 megawatt. So the cooling efficiency, now we're considering 100% DX systems. It's just for design purposes. We could use 50% of chill water then the design considerations change. Because for cooling DX units, cooling efficiency is 1, so you need 41.03. 41.03, or you can say 4103 kilowatt or 4.1 megawatt. So you need to have a cooling efficiency of 4.1 megawatt to cool 4.1 megawatt of the load. Okay, so at least we figured out the cooling load and the amount of cooling required to cool down the total load. The final estimate, total estimate, considering the critical load 2200, future load 660 kilowatt, adjustment for peak power 143, UPS battery inefficiency is 900 kilowatt, lighting load 200 kilowatt, considering 2 watts per square feet, cooling is 4100 kilowatt, and then total power required 8200 kilowatt. If you add all of them, that becomes about 8.2 megawatt, 8.2 10 raised to 6, 8.2 megawatt. Total utility estimated total. Now, when you are calculating and you are actually requesting the power company or the utility company to provide a new data center, you need to give them a figure. They're going to ask you, what is the amount of power needed? And we need to also kind of give them a near approximate estimate with the designs, considering the future loads and the future additions. You need to give them a number, and that number you are going to calculate the total power, which we just figured out, 8.2 megawatt times 125%. Adding 25 extra, that's important, because when you give to your utility company, you always add 25% extra. So your total power times 125 is 10.25. So original we got 8.2, but when you are designing and giving it to the utility company and you're requesting them, you need 10.25 megawatt because you are adding in. So when you tell them that you need 10.25 megawatt is the power required to run the data center. So you are adding 25% extra, and we need 10.25 megawatt to run 100,000 square feet with 1,000 racks data center. This is the power consumption. So that's the power requirement for 100,000 square feet. So that's a basic design. So if you have 200,000, and we have only taken up 4 servers, so you could have 400 servers or 1,000 servers. So based on the load and the power requirements increase. So now that's the ideal condition, that the power utility company is supplying the power. But what happens if there's a loss of power? Something goes wrong with the power circuit, something trips. So what we need to do is to have backup. Generator is a backup which can run the data center until the power utility company fixes their problems. So in the meantime, from the point of loss of power to the data center to the time the generator starts, something should keep the systems and the servers running. And that's where the UPS comes in. So I'm just adding a point. So UPS keep the servers running for a short duration of time. So until the time the generators kick in and they take over, until the time the power is restored back to the normal from the utility company. So for generator calculations, so what is the size of generator required? Obvious question. So we'll need generator to manage 2 loads, critical load and the cooling load. Correct? So critical load is from the servers, racks, lighting, the XYZ items which keep the data center running. And then the cooling load. Basically, you need to have a mechanical system which runs and cools the systems. So we need generator to manage these 2, critical load and the cooling loads. So we have the critical load is 4100 and the cooling load is 4100. Now remember this, when we are designing a generator for a critical load, which is only the equipment, servers, racks, the other equipments, we are multiplying 1.3. So 4100 times 1.3 gives us 5.3 megawatts. For the cooling load, we are multiplying 1.55. I'll explain it in my future videos why we are using 1.3 multiplication factor for cooling load and 1.55, 1.3 for critical load, 1.55 for cooling load. 4100 times 1.55 is 6.3 megawatts. So you add 5.3 to 6 plus 6.3, you have 11.6 megawatts. So we have to select a generator which has a rating to handle 12.5 to 13.75 megawatts. So that is the size of the generator required. Usually, if having one generator, or you can have one generator, or you can have four generators of 4 megawatts, so that even if one fails, you have three running, you still be supplying 12 megawatts. So we have four smaller generators managing to provide 3 to 4 megawatts per generator. Okay, so that's the generator calculator. Remember, for generator critical cooling load, you multiply the critical load with 1.3, and for cooling load, you multiply the critical load cooling load with 1.55. Thank you.